Hi guys. So this is the sort of part, I guess it's going to be part three, depending on how I set up these videos. But this is the part where we actually implement the Python library I'm working on. I'm sorry, my microphone setup is kind of cooked, so I'm actually using a web camera, which has a microphone in it. Um, and so I'm going to share my screen in a sec, and then we're going to get to implementing it. So what this is going to involve, just as a sort of heads up, is going to be the source code, this C++ source code for the library. And then I'm going to show how to like put it, into a proper Python library, and then we're going to install it in a Python virtual environment so that, we can see how it works and stuff. I wrote some of this beforehand, just an FYI, and this is all going to be in my GitHub repository, which I'm going to link at the bottom. But and I might occasionally do something really loud. I'm sorry. Um, but yeah, there are some very important notes here. First of all, like as you're developing this, I did this when I started, but it's not advised that you just put it sort of directly on your device without using a. My roommate just coughed loud as hell. Holy, it's so loud. Um, don't put this just directly on your device. You should be fine because, you could have issues with other Python packages and stuff. So a virtual environment is great. And I'll show how I do all of that. Hang on. Let me my screen. Okay, and now we should be good to go. So what's the structure of this, right? There is the source code that we're working with. That source code is going to have the C++ side, the Python side, um, the kernels. So let's start with the source code. It's generally recommended. I've been told to do the source code first. So let's start there. So new terminal. We're just gonna call this. Well, okay, actually, this is a really good point. Before we start, it can be really super helpful to use. I think it's like what C++ IntelliSense for bugging issues like that. Um, one of the issues I've run into in the past, right? Because I don't use PyBind for this. I use the Python header files. If you want support for that, then you have to edit your C++ properties JSON file. So I think that's going to be, was it Control Shift P, edit configurations, I think. Let's see. Yeah, and that should take us to here. Then all you have to do is add the relevant information for the Python header files that you're working with. So I have Python 3.10 installed, so I'm just going to add that. So that involves adding user include Python 3.10 and user include Python 3.10 internal. Okay, and then from there, let's do some of the actual implementing. This is not strictly necessary. This is just so if you're using IntelliSense, which I think a lot of people do, then you can see like all your includes will sort of be correct and you won't get the like include errors, can't find Python header. Okay, so let's do source, cdsrc. I'm going to put this all in a folder called OpenCL lib. Okay. Now from there, we have to make a folder for our C++ side and a folder for our Python side. So let's do make dir C++. Right, so now we have both of those. Fantastic. Let's do the C++ side first. Or actually, let's do the Python side first, because that's... Never mind. I lied. I lied. Don't listen to me. Let's do the C++ side first. So do C++, and then we're going to do kernels. Awesome. cd kernels, and then we're going to touch NCL. Okay. OpenCL by default sort of looks for a .cl file for your kernel. So we have to name them all accordingly. You know, we're doing element-wise addition, subtraction, multiplication, division. And so that's the sort of naming convention we're going to use for this. Pretty straightforward. Let's implement these now. So this, remember that global conversation we had, right? There's some things that we want available to the entire kernel. And so that's going to be, in this case, our buffers, which we're going to load in. So the way that OpenCL works is it has these buffers that store your information. You pass those into your kernel, or sorry, a reference to those into your kernel. And then from there, it will do the operations on those directly. So kernel void. I'm going to call these all by the same name, and I'll explain why later. Now we have to give our parameters, which are going to be the buffers and the dimensions of the matrices we're working with. That was embarrassing. Okay, B, and this is not going to be const because we're going to write to this one. This one is going to be C, const int rows, const int calls. Okay, easy enough. Now we write the sort of logic for the kernel. So int row equals int ID 0. So let's break down what's sort of going on with this part. This is just getting the rows and columns we're going to use specifically for this a given sort of execution unit of the kernel. And then here we have to do some type checking to make sure we're still within bounds. And then what we do here, right, IDX, because this is flattened, if you will, right? You can think of it as a matrix that's flattened. If you have the X and Y sort of coordinates of it, then you can use this equation to calculate what position in the flattened out matrix that actually is. And then this is just doing the basic operation. Now I'm going to just sort of copy over some of them because I already wrote part of this. And because like subtraction is going to be pretty much the same thing, but just with subtraction, right? So that's subtraction done. Multiplication is going to be the same. And then division is slightly different. Here we have to add some other just quick safety checks in case we try to divide by 0, because that would be bad. So here's our safety checks. So that's should be all of our kernels written. Let's start writing the rest of it. So now there are sort of a couple of components we're going to be working with here. We have to define a matrix type in C++. The reason for this is because if you wanted to convert, like, let's say a list into a matrix, that's a pretty expensive operation. And so you want to avoid doing that if you're going to do multiple operations consecutively. And so what that requires is creating a sort of C++ defined matrix type that will move much faster, if you will. And so if we have that, then we can do back-to-back operations with there, and we never really have to convert between C++ and Python as far as that set of data goes until the end. We don't have to do all these like intermediary transitions because that would suck time-wise. So let's do okay. Let's define the matrix type. So let's give me matrix.hpp. And then we have to do a couple of other things. We're going to have a kernel manager, which is going to try to determine which kernel we use and give us the path to that one so we can load it in. That's cool. We are going to need a operation manager, that's what I call it, which will sort of do the full like loading into the buffers and execution. And we also need to define our operation types that we can do, which that's quick. And then I also made a precompiled header, which I think helps. So let's get into that really quickly. This is going to be a simple class. Okay. So privately, it's going to have a pointer to our data. Right? We're doing a matrix, so it has data, it has a height, and it has width. Now we just need constructor, destructor, and some getters for all of that. So I'm just gonna kind of copy those all over. Those are pretty easy. Constructor, simple enough, destructor, and then some getters. For anyone who's not really a C++ user, maybe you're coming from the Python side, in classes, which are, very common in C++, not common in C, because C doesn't have classes. Not all information is available for outside access. So if you want to access it from like another class, if you want to access it from like main, whatever, right? This is not all going to be immediately available to you. Like you can't just do like object dot quality the way you would in Python, right? You have to use these functions, which will sort of regulate access. Now we're going to define our kernel manager. That's fun. Our kernel manager. Well, actually, let's do I lied. Let's do our operation types first. This one's quick. So we're gonna define it. This is an enumerated class. Why are we using this? Is it optimal? To be honest, I'm not sure. But I have grown to like switch case. So, and let's see, do we use switch case in this? Whether you okay, so you can use switch case for this, and that can be useful. But I also like this because you can use it as a map, like to sort of map keys onto values. And this is, I think, pretty readable. So let's do this. Okay. There are a bunch of includes sort of involved in this. I'm going to put them all in. So we're going to include those types because we have to map a specific type of operation. Like if we want to do an add operation, that's going to map onto a different kernel, right? It's going to map onto the add kernel. So I'm going to show all of that in a second. And then there's just some other things we're going to have to show. It could make sense, I think, to use a struct to sort of show your kernel source info. Because what's going to happen is your source code, right? The source code for the kernel is going to go into a const char pointer, and that's going to have a given length. And so it could be useful to put those all into one struct. For people coming from Python, structs are like Okay, and if you're like a really experienced C++ dev, don't roast me, but what I was told by my professor, who admittedly was not very good, is that, you know what? Ignore me. Don't ignore what I just said. I'm gonna maybe try to edit that out. Um, this is a learning experience. I'm learning with you. Let me just Google this. Google something really quickly before I get this wrong. Okay, yeah. Okay, so that's what I thought. Um, what I was going to say was that structs and classes are very similar, but in classes, right, you have that public and private. So private fields cannot be accessed from the outside without some sort of getter or friend declaration. But structs have all of their members as public by default. So that's more similar to like Python. I don't know why I second guessed myself on that. That's what I thought originally, but I don't know, whatever. As far as the kernel source info, that's not something that we're really worried about outside groups accessing because we actually want to, be able to show that off to other classes. So we're going to do that as a struct. So this is our source, size key length. Okay. Kernel source info. Okay. So there is an associated method with this class, which will just get our source info for us, depending on what operation type we're using. We're also going to have a lookup table. So like this operation will map onto this specific location. And we're also going to, and this could be fairly large in the figurative way, but it could be worth storing these kernel sources if we're going to use them again somewhere. So let's get into all of that. Um, okay, in here, we're going to put a mapping between the operation types and the relevant file location. Actually, okay, just as a quick note, for any, I was not originally a programmer slash CS person. I came from mechanical engineering. I, was kind of on that side of STEM, like through all of high school. I didn't even start programming until like really like sophomore year of college, and I'm now a senior. So that's comparatively much less experience than some other people, but I am trying. Um, for anyone who did not figure out multi-line editing until way too late, it's going to be you start from the line you want, Control Alt, and then down the arrows. You can select multiple lines. We have four relevant kernels, four relevant operations. So we're going to do operation types. They'll all be add for now, but I'm going to change that in a sec. These are going to be in source, OpenCL lib, cpp, kernels, dot cl. Now, okay, you might be thinking, wait, but that's not the right directory, right? Wouldn't it just be kernels and then whatever thing? And you know what? That would make sense. But the thing is, it's getting called from outside of source. So you have to give the full directory. Let's change these now. Now we just need to add a sort of cache for our kernel sources, because if we already sort of go through the trouble of putting those into strings, we don't want to do that too many times because that could be expensive. Okay. So, all right. Now let's implement our get kernel source. As a quick note to anyone who okay, so for anyone who comes from Python and doesn't really understand these like .hpp, .cpp files, right? In Python, you write a file, you just sort of do like import whatever that file is, whatever, class. Here, you have to break it up into your .hpp, .cpp files, so your headers and then your sort of implementations. The headers are what you can include, and you can put definitions for them in your .cpp files. This is specifying, like, okay, if I just wrote get, just so this is just more as a note to the Python people. If I have get kernel source, or no, wait, sorry, not get kernel source. No, it is get kernel source. Okay. If I have this, so this is going to return kernel source info struct. I get kernel source here. Operation types. Okay. What's the problem here? Right. This is unidentified. You have to specify that it's returning a member type. So that's going to look like this. Okay. Easy enough. What is this? Constant not allowed on a non-member function. Problem is, it doesn't know that this is part of the implementation of the kernel manager. So we actually have to specify this as well. Now we are good. So let's do the implementation for this really quickly. Also, just as a quick C++ note, auto, right? When I was learning about C++, in my object-oriented programming class, he was a professor, right? Big, think like big, like 6'2" white guy, long beard, scary dude. I mean, he's like he was one of those like I'm sorry, I'm gonna yap for a sec. He's one of those like old school, like, oh, I only use Emacs. I fucking most of my career was writing x86 assembly. VS Code is for losers. Like he comes from like that sort of older generation, and I don't know, he was not a big fan of Auto, but Auto is fine. Auto just basically looks at what this is going to return and then sets the type for this accordingly. For the most part, it's actually pretty good for performance. Whoops. Especially if like the type you're going to work with is some like really long structured like an unordered map of um if you're gonna like if the type you're assigning into is gonna be like an unordered map of like some type you just came up with to some other type you just came up with, then auto is great. Nation equals lookup table dot end. So this is checking to see if we did not find the kernel. So we're gonna throw a runtime error. So if you don't find what you're looking for, let's throw an error. By the way, that professor who I mentioned, he is like one of my favorite professors, by the way. That wasn't slander. He's just a really old school guy. He looks like if you can imagine it, he sort of looks like a really mean Dumbledore, but he's like one of the most knowledgeable people I've ever met. And two, like because I had him for a class where there was like object oriented programming was taught in C++, plus plus, and that was a required course. But the thing is, if you have him in a class where it's like optional to, to take it and it's a little more challenging, like programming wise, then he's a lot nicer. Let me check something quickly. I just want to make sure Zoom call is okay. Yep. Okay. Wow, those are all the possible layouts. Okay, whatever. That's that's fine. Okay, so existing source equals kernel sources dot find mission type. Okay, so we're gonna see if it's actually been loaded. If equals kernel sources dot end. So if it has not been loaded, then we're gonna load it. IF stream file. So then we're going, if it does not open, you gotta throw an error. One of the one of the things that professor told me, which is really good programming advice, is that if you ever do a sort of library call or a yeah, okay. If you do a library call or anything that could, really fail and blow up in your face, you should do a check to make sure that it works properly and, output something if it failed. So we're going to load it into a string buffer, and then we're going to close the file. What is the error here? No operator matches these commands. Oh, sorry, this should be a string. Whoops. Silly me. Okay, then we're going to close the file, and then we're going to insert into our source. We're going to insert entry, which is going to be our op type, and then this. Kernel sources. Whoops. Okay, and we're good. Now we just have to update the pointer to the persistent string data. Current source equals kernel sources dot at type c string. Source. Okay. Like that. And then now we just got to load all this information into our struct that we made. Oh my God, I can't spell worth a damn. Okay, so that is our kernel manager done. And so now let's do the, actually, let's do a precompiled header real quickly. I don't even really say, you know what? No, I lied. No precompiled header. Didn't need it. There's not really much time. Like it's so small that we don't really get time savings out of it. So I don't really see a point. A precompiled header though is useful if you're gonna have to include like several libraries over and over again. Do touch. Okay. It's over. Okay. Oh man, I've been recording this wrong. Let's do it like that. Okay. Um, that was a mistake. I'm sorry. I'm relatively new to doing this, but just I'm gonna go over everything really quickly in case you couldn't see it before, including relevant Python stuff. It's important. This is what our kernels look like. So our floats here, rows and columns. I don't know if you had to zoom in before or whatever. My apologies. Adding, determining our position in the buffer. Some more safety checks here for division. You can pause this at will. Multiplication, subtraction. Our file structure is source, and then that has OpenCL lib folder inside, and then C++ and Python. Then those, I haven't put anything in Python yet. C++, right? Kernels directory. It's got all these kernels in it. Let's go over this really quickly. I feel really bad now because I thought that was recording better before. Okay. Checking to see if we already have the kernel loaded or if the kernel, sorry, if the kernel exists. We check to see if it's in our cache, and then we read it and then put it into a kernel source info struct. And this is our lookup table here. Get kernel source is the method we defined. This is our struct for it. And these are our private members. This is how I define matrix with the getters. And now we're going to do, oh, and this is operation types. So we just defined 4 types here. Or sorry, no, let me be very specific with the language. We define 1 class here. That class has, I guess, 4 items in it. So with this enum keyword, it changes it from like a normal class to a, it's almost like, I don't want to butcher this explanation, but my understanding is like all of these map onto a number. So like 1, 2, 3, or 4. And then you can use switch case for them based on that. Let's do operation manager now. Fine. Include a vector, and then include, we need the kernel manager. Operation types. And the big thing we need to include here is the OpenCL library. And the header file for the OpenCL library, and that way we can work with the stuff in it. Okay, let's get to the implementation of this part. So did not need that many empty lines. Operation. Okay. You can use a CPU or a GPU here. I am going to set it so by default it uses the CPU because, if you have a computer, right, it's basically guaranteed to have a CPU. It's not guaranteed to have a GPU. A lot of computers don't, or they have like integrated graphics or things like that. You're not guaranteed to have access to a GPU. So that's okay. You'll still get a lot of benefit from doing this because your CPU will run faster here. Let me be more specific with that. Even if you have to do CPU-based operations, that's still going to be faster than doing them in Python. So let's specify our device types. Constructor, destructor. For anyone else who's coming from the Python side, right, this is something that Python normally just takes care of for you automatically. But in C++, if I allocate memory, which we are going to do, then that's not going to sort of, that doesn't just deal with itself the way it does in Python. Like in Python, if you make a list, once that list goes out of scope, Python just takes it all down for you. That doesn't happen in C++. And so we need to call a constructor, which will, allocate memory or do whatever we want when we're creating the object, and then a destructor to free up that memory once we're done. This is our sort of big hitter. So we have to specify operation type. So we have to know what the dimensions we're working with are going to be. We need the data for the left-hand side and the right-hand side. So that's like if we have like, matrix X is going to be equal to Y plus Z, then Y would be our left-hand side and Z would be our right-hand side. And then we have some private members. So we need a kernel manager so we can get, the kernel source. And then there's some OpenCL specific stuff. So the platform information, device ID. So that's gonna be like CPU or GPU, CL. We need to know the number of platforms. It's gonna be our context, and this is gonna be our queue. And that, what am I missing? Oh, colon here. And that should be it for our header file for our operation manager. So now we just have to do the, operation manager part of it. Okay. I'm going to copy and paste something which, I use to debug. It's essentially just a huge function, which I will admit I did not write. ChatGPT wrote it. Love you. Huge function which contains like all the various error codes that you can see with OpenCL. So yeah, take a look at this. This is dense, right? CL success, device not found, all these various issues you can run into, which are great for debugging. These are going to be in the files as well. Now let's do our constructor and destructor. We have one entry. We already specified a platform. We specified a number of platforms, or I guess a reference to it. Okay. Now here's why I love switch case. Should not be CL device type. It should just be device type. Okay. One case is that we're working with a CPU, so that's fine. In that case, we're going to do CL get device ID. And then it'll know we're working with CPU. Reference to device. Sorry, not reference to device. Okay. In that case, we have to pass those in. I'm missing something. Oh, yeah, wait, you don't use, my apologies, you don't use those for switch case. Is the error here? Expected. Oh, whoops. Okay, and in the event that we're using a GPU, I put a little bit of error handling here, because even if you call it and say you want to use a GPU, you might not actually have access to one. So in that case, we're just going to sort of default to a CPU. Okay. If this fails, and actually I should do that here too. Hang on, because it is a library call. Do uh enable to get CPU device ID. Yeah. And here we're gonna do that. And now, okay, I accept that this is not pretty, but I'm just gonna put this here for now. Actually, no, this is super, super ugly. Uh, but you know what? Fuck it, I don't care. Um, but you know, this level of nesting is, I agree, suboptimal, but we have other things to worry about, and it's late, and I want to have dinner. So context equals CL create context null one nice null null null. Okay, so this is initializing our context, initializing our command queue, so we have to pass in our context, the device information, and other details. Now let's work on our destructor. Oh, so once this is over, we have to release our command queue. And we have to release our context. Okay. Now all that's left to do is implement the logic for the element-wise operation. I do the CL int error just because we're going to do a lot of that, like this sort of error checking. Super, super useful to know when things go wrong. Let's get the kernel info. So this is calling the get kernel source thing that we defined before. Sorry, that thing method. Now we got to create our program. Okay, so this is passing in our source and passing in our context, and now create our program. Note here, right, for the error checking, we pass in that variable, so then we can check against that to see if it failed. So if there is not CL success, then throw SD. Okay. Now we're going to build our program. So okay, just a big note, right? Some of these methods return like, some sort of error code. Some of them take the error value in as a parameter. So I don't understand why, but I guess that was a decision that was made. So we have to check this as well. We'll just do, if it fails to build the program for whatever reason, this is sort of a good place to stop. Because, right, if creating the program fails, then building the program is kind of also guaranteed to fail. So if that's the case, then we're going to release the program. But it's not bad. It's not a bad idea to get some log info. So CL get program build info. Okay, now we have to get the build info. Program. Yeah. Whoops. Log size, and then we need the data. Yeah. You know what? I lied. Let's just keep it simple. Forget all that. Let's just throw in error. Runtime error. I didn't. Okay. Just a disclaimer. I did not say I was a professional. Failed to build program. Uh, no. I lied again. We are gonna include all of that. So release program. So we do have to release the program. That's pretty huge. And then I'm going to throw an error, and we're going to include specific information related to that error by converting our build log data to a string. And then we're going to display that. And passed it. Now we have to make our kernel. So we have to call CL create kernel, take in our program. Okay, this part right here caused me some strife, and this is why. You could, in theory, right, and this might be sort of the smart thing to do. You can put multiple kernels in the same file, and then I'm not, because I want this to be like sort of more readable, but probably the better way to do it is to put them all in one kernel, especially if they have like similar usage, if you will. So like if I was, doing other crazy matrix stuff like Frobenius norm, whatever, then that would probably warrant a different kernel. But element-wise operations can all go in the same one. This here specifies the name of the specific kernel, like function you want to use. I named them all op kernels, so this isn't a problem, but normally you probably want like, called to, or you try to get it from somewhere else, like dynamically, if you will. Okay. If error is not CL success, so it fails, CL release program, always release the program if it fails, and then with a runtime error, failed to create a kernel. Get OpenCL error string. Cool. Now comes sort of the meat and potatoes of actually doing the computation. So we have to define our matrix size, which is going to be known at runtime. In this case, we're working with floats. So our matrix result is going to go in a okay. So let's talk about what this is for a sec, right? Malloc. Some of you guys might, if coming from oops, if you're coming from the Python side, you would not have seen malloc. I think it stands for memory allocate. Pretty sure that's logically that's what it would be, right? If I want to allocate, certain amount of space in memory, then I have to call malloc. And malloc takes two parameters. One, you have to define what type you want. A float is 8 bytes. So this will know to sort of allocate in like multiples of 8, if you will. So I can store bytes nice and evenly. And then also takes in matrix.size. So you have to know like what size your sort of unit's going to be. In this case, it's a float. And how many of those units to allocate. Easy enough. Just in case, malloc, if it fails for any reason, we will never know. It returns a null pointer. So this checks to see if it returned null pointer. Like it will either return a pointer like with whatever type associated, whatever type we're using. In this case, it's float. It'll return that kind of pointer, which will be the first location in the allocated memory. But if it fails, it'll return a null pointer. So we're checking for that. Okay, we're only have to use buffers. So what we're going to do is load all of the data from our floats, from our arrays into the buffer, do the computation, and then we have to put that result in from result buffer back into our matrix result that we allocated. So let's create these buffers. Meme. Read only. Okay, what's this doing? Um, this takes in our context to help create the buffer. We're specifying read-only privileges for it, right? Because the LHS and RHS buffer we're not going to write to pass in the size of them, and then the data. There should be a comma there. Okay. And because we're passing the error thing in, let's, do some checking here. LHS and RHS are both going to be pretty similar. So LHS, well, actually, they're going to be exactly identical, and we're just going to change literally one letter. And then result is going to be a little different because result is going to have write privileges. Mem write only matrix sign. Yep. Okay. Failed to create buffers. Let's do LHS here. Okay. Cool. That was easy. Now we have to set our kernel arguments. Right, let's take a look back at our kernels, right? They took these arguments, and so we have to put those in accordingly. Kernel 0 size of CL LHS buffer. Cool. We have to do one for RHS. Let me just check something really quickly so I don't give a sort of botched explanation of it. Oh, okay. Do the, I'll do this as multi-line, right? Uh, there's gonna be some number there. Size of something is going to go in there. And then reference to some other stuff is going to go in there. Okay. So this will be 1, 2, 3, 4, right? To represent our different possible arguments. This is also going to be CLMM. And these are both going to be ints. This is going to be our result buffer here. Now, 1 second. Okay. All right. So now we just have to do a check to see if our kernel arguments failed. So that's going to throw SD runtime error. Fail to set kernel arguments. Cool. Okay. Now we have to determine our global work size. So the global work size, my current understanding is that that sort of defines that will define the dimensions that our CPU or GPU has to operate in, and will sort of do the I guess was it allocate cores accordingly. Someone correct me if that's wrong, please. But actually, you know what? I really want to make sure I get this right. Okay, right, my bad. So it refers to the specific number of work items, which I mentioned before. Those are threads which will execute in parallel across all compute units. Okay, so I'm gonna give myself a B plus on that. It defines the problem space or how many operations your, I guess, computational device, if you will, is gonna have to run. Maybe not B plus. Let's go C minus. Uh, global work size. It's gonna be two-dimensional in this case. It can be three-dimensional. Okay, now let's do some executing, right? In order to execute this, we have to pass in our Q, our kernel, dimensions, work size. All right, all of this. And then if it fails, then we want to give a message. So throw a runtime error that we failed to execute the kernel. Awesome. Now, once that's executed, we have to put the results into our result buffer. No, I lied. Not put them into the result buffer. Sorry, I misspoke. Put them from our result buffer into our allocated memory that we put for results. I think it's yeah, here, matrix result. You gotta put that information in there. Height times width times size of float. So specifying the size, specifying what we're doing, like where we're putting it. Awesome. And if that fails, then that means we failed to read our results. So again, you gotta throw a runtime error. And now there's some relevant cleanup. So we have to release our buffers. We have to release our kernel and our program. And then finally, we just have to return our matrix result. And that's done. That's all of the C++ source code for doing some basic computation. And now we just have to do the bindings. So the bindings define the interface between the Python and C++ side, and it'll sort of define how we're gonna call stuff through Python. So let's go into Python. cd and we're gonna call this bindings cpp. Okay, cool. Let's go into here. This file it tends to be pretty verbose, so stick with me. Probably gonna be about like, smooth 200 lines, but whatever. I like yapping, I'm a big yapper. So we have to include the Python header files. Have to include struct member, and then we have to include the stuff we defined. So that's going to be the operation, and that's going to be matrix. Cool. Let's do a matrix wrapper. Necessary. This is a wrapper for a defined pi matrix type. And now we have to do some initialization. Sorry, let me be clear. There's going to be some methods that this is going to require. And so we have to sort of define all of that interface in the Python side. So let's actually start with deallocating it once it goes out of scope. Matrix dealloc. Okay. This will take in a pi matrix object and it will delete the matrix that exists in it. And then we have to free it. Oh, static. Now we have to do the new function. I reverted back to my old ways. I'm trying to get more used to the sort of C syntax, or C, not syntax, but way of writing things. And so you're supposed to put the asterisk on the variable side. Bruh. This is allocating the space for this on the Python side, I believe. Someone correct me if that is wrong. Okay. Now we have to initialize it. There's some kind of weird stuff involved in this. Well, I guess weird for me since I haven't been working with this super long, but I'll sort of try to walk you through it. Okay. Yeah. AWDS refers to it's sort of similar to keyword arguments. It collects the keywords into a dictionary, and then you can do some work with it. Okay. So now we have to define our data object. We have to read in the height and width. So this requires parsing the arguments. They do it really weird here. Like, sorry, this is the way of doing it. It's just foreign to me. You have to specify what the types are going to be by using this like weird, I guess, Python terms, it would be a string. In order to specify what it's going to look for. So big O specifies the object, and then the I specify integers. It's variable length. I guess it doesn't, want to do that. Like you can't do this part at runtime unless you have this, I guess. So that's why they made that choice. If that fails, then we want to give an error because we want this first argument to be a list. We need the size that we're working with. And then we have to do some checking for that. So if size is not equal to height times the width, then we want to throw an error. Okay. And for all these errors, we're going to be returning -1 if they fail. I'm missing one here. Sweet. Oh my God, I still have so many lines I have to write. That's okay though. I'm gonna at some point give up and start copying and pasting. We have to allocate okay, big note, right? I used malloc before. I come from C. That's what I'm used to. You can also use new. It's really the same thing, but more, I guess, reader friendly now on the C++ side. So let's just use malloc anyway, right? Float. Give you a float pointer, malloc, and then size. I lied. New is growing on me, so I can use that. I am aware I should pick one and stick to it in the future. Now we just have to transfer all of our items over. Whoops. Okay. So now we have to get the items. So that's in data object and I. Now we have to create a new matrix with all of this information in it, and then we'll return 0 because it worked. Okay, now at this point, my hands hurt a little bit because I've done a lot of typing. So I'm going to do a little bit of copy and paste, but I'll still sort of try to talk through it. We have to make a getter for this, and that's going to look like this. So initial, like copy the data into an array, you know what the size is going to be, and then you sort of create a list based on this, and then you return it. Easy enough. And then here we have to define the methods that we're going to have for our matrix. So that's really just get data. And this is going to be some relevant information about what the Python interface is going to look like. And sort of take a look at this. Okay. Now here is the much longer, but I guess not super long one. Right, we defined this struct for the matrix, and so now we have to do everything for the operation manager. So we're going to have a similar relevant struct for it, right? My operation manager still needs the dialog, which is just going to call the destructor that we defined for the operation manager. Still need the new, it's going to be the same. Its initialization is a little different, and I'm gonna type this one out. Static int iteration I object. So we're still taking in, you know, variable parameters, keyword args. Okay. Char device type string. So this is going to be a representation of what device we're using. So if you still have to do that sort of parsing with that string involved in what the in this case, we're just taking in a single string, so you only need the S. And then we have to define our device type. Okay. So if it's a CPU, then we have to set that. And if it's a GPU, we have to try to set that. Okay. That's cool. Now, we have to create a new operation manager instance with that parameter specified. And that's it. Okay. Easy enough. I'm sorry, my roommate's making a lot of noise. I don't know if you guys can hear that in the recording. Okay. Now we have to do the interface for the main operation. Okay, so take some arguments. Take a string for the operation type, and it should take two pi matrix types for the left-hand side and the right-hand side. Now, if we have to parse this tuple again, by the way. So it takes in a string for the operation type, And I guess if we look at this, right, takes in some float pointers and some integers. Now, we called it that way, but that doesn't, I guess, exactly match. That doesn't exactly match this. I already wrote this anyway, and I know it works, so I'm going to keep it. But this takes in, right, two arrays and then the dimensions. I defined the interface a little differently, which is fine. Because at this point, I am super tired. So it takes a string, I matrix type, HS, the matrix, HS. Okay. My roommate is so loud. Jesus Christ. Okay, sorry, he's being really loud, but that's fine. I'm only allowing this because I'm also sometimes a terrible roommate. Okay, so we have our operation type, and then now we just have to check to see what operation we're trying to pass in, and then we'll set our operation type accordingly. So if it's add, then we'll do add, sub, mul, div. Easy enough. Now we just have to set some of our other relevant information. So we have to call, or I'm sorry, not setting relevant information. Call the element-wise operation method that we've defined, pass in all of the parameters for it, and then we have to convert that result back into a Python list, which is going to look like this. They're having an insane argument in the next room over. Result list here, right? This is going to be a Python list. We have to pass in our dimensions and the results. We have to copy over the results individually. Once that's done, we just not here, sorry. The result, return the result list. Okay, that's pretty easy. To define the methods for it, right? We just have one, that's the element-wise operation. Here I'm specifying some, again, the related information for it, the size of it, how we're going to call it. Okay. Now we just have to do the initialization for the module. So static module def. Maybe we can call it matrix module. Okay. Module def head init. Call this, let's call this sample OpenCL and quick description, matrix operations module. One, then null. Okay. This is the last step in defining this. So this is just adding the objects that we'd possibly need to this library and making sure that's all ready so we can do the actual setup part. Is she, I don't know if she's like tickling him or what's going on, but this is like actually horrid to listen to. Okay. Okay. Now we're getting really close. We just have to make a make file so life doesn't suck and a setup file. So let's do the setup file first. Touch setup.py. The setup.py file sort of specifies how this whole thing is going to get built. Okay. Now, setup tools, import setup and extension, because we're building a Python extension. Assist, import OS. Okay, awesome. Python include this executable dot replace. Okay. We have to find Python installation. I'm doing this as a formatted string, just so like whichever Python version you have will be supported. If you're not using 3.10, I am sys.version info.major sys.version info.minor. So this is getting like, if I'm using 3.10, then major is going to be 3 and minor is going to be 10. What's this? Oh, whoops. Awesome. Okay. Now we have to define our CPP extension. So if you do this minimally, it still takes a bunch of arguments. Has a name, which is going to be sample OpenCL library, right? That's how I defined it here. Yep. Awesome. Okay, so I have a name for it. I have my source code, which is going to be src. Actually, a lot of these are the same, so I'm going to do multi-line edit. src slash open c, whoops, clib. Okay, that's pretty much where all the similarities end. Okay, so these are both similar, and this is going to be the kernel manager, which we need. Oh, and we also need our bindings. So this is going to be in Python and then bindings.c++. Awesome. Cool. Now we need our include directories. So that's going to be our Python include and src openclib cpp. This is where our header files are. Fantastic. Libraries are going to be OpenCL. Stick. Okay, yeah. Language, we have to specify we're using C++. And now we need some extra compile arguments. C++ 11, using a slightly older version, but whatever. Oh, don't know why that auto-corrected like that. open this. You never realize how annoying your roommates are until you need them to not be annoying. No, I love them to death. I'm just joking, but true. Okay, we need position independent code, so I have to add the FDIC flag, and that should be good. This just means that Python macros can generate unused functions. Okay, now we just need to do setup. Whoops. Name sample OpenCL library version. We're just going to call this 0.1 and this is going to be our extension module. This is basically it. Now, in order to make this work a little better, or sorry, just to make life not suck, let's write a makefile. So if you're not familiar with makefiles, they allow you to sort of, like, if I have to build something, and I know I'm going to have to run this set of commands over and over again, it lets you condense all of those into just one command. Remember I mentioned we're going to put this in a virtual environment, right? So I have to specify that. I have to specify Python information. These are going to be the commands you can use. Sorry, not representation. Ignore that one. Actually, representation's cool. Let me quickly just kind of copy this in. New file, directory, .py. The source code for this is also going to be in there. If anyone who's ever used Claude, right? Claude AI, I really like the feature where it sort of creates the tree out for you and displays it. And so I had it write some code that'll do that. So if I run make representation, then it'll sort of give a tree view of what the overall directory looks like. So this will just run representation. Just gonna call Python 3 directory 3.py. Okay, so just so you can see it, if I do make representation, right? This is what the structure of our project looks like. I really like that. I think it's pretty useful. Show off what we're working with. Okay, so because it sort of recursively goes through all of your folders and just prints out the content. We have to set up our virtual environment. So env Python m. Okay. And then these two are just to sort of support the installation of our library. Awesome. Where are you? No, I never. Hang on. Yeah, okay. Ignore that. We're not using numerical Python, although numerical Python is a fantastic library. Okay. Awesome. This just means that if I run all, then this is going to be a dependency of it. That should be fine. Clean. There's a lot of build artifacts associated with this, and so if I run clean, that'll just sort of get rid of all of them. And then all that's left is test. So in order to test, I have to have my virtual environment set up. and then it will just run. I want to run our test.py. So env name in activate, and we're going to run Python, and let's do test.py. So now I have to specify our test.py. Okay. For test.py, we're going to import sample OpenCL library. Awesome. And then we'll just do basic stuff, right? Some small matrices. That's cute. What are the problems here? Oh, sorry, I'm copying this over from some other test cases I wrote. Okay, so now we have our, isn't closed. Oh, missing some commas here. Okay, sorry, I was missing some commas there. Okay, so we're just about done. Now we're going to do some basic operations. So let's do add. Oops, let's do this instead. Okay. Sample OpenCL lib dot. Okay, element was operation. Should be good. And then we'll just do print result dot get data. That should be it. Let's hope really quickly. Let's just make representation again to see project. Okay, that looks good. We like that. And now, just to show it off, right? This will run all of these commands. It says that, OpenCL lib's not installed, which is fine. Okay, let's just do make. So this is creating a virtual environment. What is this error? Concept not run successfully. Extension init is missing one or more sources. There we go. Oh, where are these errors? God, I love error checking. Okay. So the issue, if we look at it, sorry, I had to pause the recording to go to the bathroom. Definitely not to do any error checking or any investigation. Let's do OpenCL int error here. And let's get rid of these initializations. Okay, that should be part of it. Actually, that should be all of it. Info. Let's check again. Oh, yeah, okay. Make clean, need all that. Make. Okay, that means we installed a library. So let's make test. Oh, sample OpenCL lib has no attribute element-wise operation. More debugging. Fantastic. I love debugging. Hang on. I'm going to go yell at my roommate because they are interrupting me, interrupting my train of thought. So, yeah, this is a pretty solid testament to how burnt out I am. You know, because I'm okay. I'm just to be clear, I'm doing this as one. Oh, that's wrong thing. Whoops. Let me. Whoops. Sorry, that's what I was reading off of before. Okay. My bad. This test was wrong. The reason it's wrong is because this is not a, just so we're clear, this is not a method of the sample OpenCL lib class. This is a method of the operation manager. So there is going to be sample OpenCL lib dot operation manager, like that. Should take in CPU device, or I think it's just, let me check our binding really quickly. Right, it should take in, okay, CPU or GPU, cool. We'll just do it with the CPU. Okay, result equals operation manager. Add, okay, small matrix 1, small matrix 2. All right, let's try this again. Make clean, make test. Oh, yeah, you are right. It should be, thank you, Python. It should be written like that. I love you, Python. I would never do anything to hurt you, Python. Even though this channel is called Lucas Loves C. Okay, make clean. All right, please. Oh, failed to create result buffers. Let me check something. Okay. I am so sleepy right now, but it's okay. I'll try to finish this. If you're looking at what I wrote right earlier, made a slight little oopsie here. This should not be LHS. This should be result buffer. Oops, happens to the best of it. Okay. List object has no attribute get data. Oh, whoops. Right. This is promising though. this should just be results. Okay, here we finally, after all that turmoil, have gotten our result. So let's just let me just sort of save myself here if you're judging me, right? Which is, I think, quite reasonable. What we did was write some source code in C++, write a sort of API for it that allows you to program through it in Python. We put that library into a virtual environment, and we ran a small test in that virtual environment. This is, I'm sure this is not the sort of industry standard of how to do it. I've just been working on it for a little bit, and I wanted to sort of get some feedback on it, which is why I'm sort of walking through my process on YouTube. If you are someone who is, more experienced with this kind of thing, please leave a comment because I'm very curious on ways that I can sort of get better with this sort of thing. I do want to become a C++ dev one day, and so this is sort of a step forward for doing that. I think my next project, once I get paid, is going to be sensor fusion because like my dream company, not to exclude anyone else, is Anduril. They do a lot of drone stuff. So the next project is probably going to be sensor fusion. I think I'm gonna get a thermal camera. I'm gonna do some cool stuff with that. Like one of the thermal camera chips. You can try to do some cool stuff with that. All of this source code is going to be on GitHub. I'll link that in the description. If you have any sort of other notes, please let me know. Thank you for watching.